Hello! This week and next week, we are going to focus on a new test called the Factorial ANOVA. The reason we're spending 2 weeks on this test is because it's the most complicated test that we've learned so far, and it's going to be the most complicated test that we've learned this semester. What makes it a little more complicated, as we'll see in a minute, is it's the only test that we're going to learn this semester that involves 3 variables. Every other test we've talked about so far only used 1 or 2 variables. This one uses 3. However, as we'll see, there's a lot of similarities between this test and the test that we've learned previously, so I wouldn't necessarily say it's harder, it's just a little more involved. So all of the tests that we've learned so far, or at least the ones we've learned recently, looked for a relationship between 2 variables. We would call those bivariate tests. We've got an x variable, which are our independent variable. We've got a y variable, which is our dependent variable. And we want to know if x is related to y. Usually what we've been doing is comparing groups against each other. The x variable tells us what the groups are. The y variable tells us the people's scores. And we're comparing the scores between groups to see if, in fact, those groups are different. In the real world, however, things are usually not that simple. We can't really go around looking at variables 2 at a time because there's a lot of variables simultaneously influencing each other all the time. So what this test is going to allow us to do today is add in a 3rd variable and study relationships and effects that are a little more complicated than what we've been able to do so far. Before last week's exam, we spent 2 weeks talking about ANOVAs. We first talked about the between subjects ANOVA. That's the one where we're comparing 3 or more separate groups of people against each other. And then we talked about the within subjects or repeated measures ANOVA, where we were comparing the same group of people across 3 or more different points in time. What both of those ANOVAs have in common is they're called one-way ANOVAs. One-way meaning we only had one independent variable. So for the between subjects ANOVA, for example, we looked at how the location of your phone affects your performance on a cognitive test. We compared 3 groups of people who differed in terms of where their phone was. That was our independent variable, and their performance on the cognitive test was the dependent variable. For the within subjects ANOVA, one of the examples we looked at was whether taking a gardening class improves people's mental health. So we measured their mental health at 4 different points in time. Our independent variable in that study would be time. Our dependent variable would be mental health. So again, in both of these types of ANOVAs that we learned recently, we have one independent variable, one dependent variable. We want to know if those 2 things are related or not. What this new test, the Factorial ANOVA, is going to allow us to do is add a second independent variable. So now we have 2 things, IV1 and IV2, that are both affecting the dependent variable, or at least we think they might be. What this will allow us to do is see whether either or both of those variables has an effect on whatever outcome it is that we're interested in measuring. As we'll see in a little while, a Factorial ANOVA is going to tell us 3 things. First, it's going to tell us whether there's a relationship between our first independent variable and the dv. Then it's going to tell us if there was a relationship between the second independent variable and the dv. And then finally, it's going to tell us whether all 3 of these variables are related to each other somehow. Another way of thinking about that is whether the combination of the 2 independent variables is affecting the dependent variable and causing it to change. We call that an interaction. We're going to talk a lot about interactions in this video and again when we meet next week, but basically an interaction means that in order to know the whole story of what's going on in this relationship, we have to know all 3 of these variables because they all play a role. One way of thinking about an interaction is that it's not either of the 2 independent variables that's affecting the dv, but it's the combination of them that affects the outcome that we're interested in. Another way of thinking about it is that the relationship between one of the independent variables and the dependent variable depends on the other independent variable. We're going to hear that phrase depends on quite a bit in these examples. And anytime we hear the phrase depends on, it's a big hint that we've probably found a significant interaction. In statistics, the word interaction is synonymous with the term moderation. So if you've ever heard people talk about moderation or moderating variables or moderators, what they're really talking about is interactions. It's just two different words for the same thing. So here's another way to think about what an interaction between three variables means. We've got our diagram here showing a relationship between x and y. X is our independent variable and y is our dependent variable. But we've also got this third variable m with an arrow pointing to that relationship between x and y. What that tells us is that there is a relationship between x and y, but the exact nature of that relationship depends on our third variable, m, which is also going to be a categorical variable in this case. Maybe, for example, x and y are related only sometimes, but not other times. And m is the variable that tells us when they are related or when they're not related. Maybe x and y are sometimes positively related or sometimes negatively related. And our moderating variable m tells us when the relationship is positive or when the relationship is negative. So m is kind of like a light switch or a dimmer switch. It tells us how strong the relationship between x and y is, or whether that relationship exists at all. It's kind of like imposing a caveat on that relationship and saying it sometimes exists and sometimes doesn't. Or it sometimes looks like this, but it sometimes looks like that. That's what we mean when we say we found an interaction. To give a simple example of this, a study from back in 1996 wanted to see if drawing a smiley face on the check actually resulted in servers getting bigger tips. So they went into a restaurant and they had some servers draw smiley faces on the check and other servers not draw smiley faces on the check. And what they found was that overall, servers who drew smiley faces on the check did in fact get bigger tips. However, then they went and took a closer look at their data. And what they found was that that only happened if the server was a woman. In other words, drawing a smiley face on the check did produce bigger tips, but only when the server was a woman, not when the server was a man. If we take those variables and we put them in the diagram on the left-hand side here, our independent variable is whether the server drew a smiley face or not, and our dependent variable is how big of a tip they got. That relationship depended on the sex of the server, and what they ultimately found is that drawing a smiley face did affect the size of a tip for women servers, but did not affect the size of tips for men servers. In other words, the relationship between drawing a smiley face and how big a tip you get depended on the sex of the server. So again, we'd call this an interaction. To talk about this in general terms, and again try to wrap our heads around how this test works, before we put any numbers to it, before we go into SPSS and actually do the test, we're going to talk about how we could do a study to figure out how to make the best possible peanut butter and jelly sandwich. Now, imagine we've got two different types of peanut butter at our house. We've got crunchy peanut butter and we've got creamy peanut butter. We've also got two types of jelly in our house. We've got grape jelly and we've got strawberry jelly. So these things are going to be our two independent variables for this thought experiment. Our first independent variable is which type of peanut butter are we going to put on the sandwich? And our second independent variable is what type of jelly are we going to put on the sandwich? If we wanted to figure out what the best possible sandwich is, what we'd have to do is look at every possible combination of the two types of peanut butter and the two types of jelly. So ultimately, we'd have to make 4 sandwiches. We'd make 2 sandwiches with crunchy peanut butter, 2 sandwiches with creamy peanut butter. Then, one of each of those would get grape jelly, and one of each of those would get strawberry jelly. So we have 2 independent variables, each with 2 levels, 2 types of peanut butter and 2 types of jelly, and we're looking at every possible combination of those things, which results in 4 potential different sandwiches we could make. So let's say we did this study. We make 400 sandwiches, we find 400 people, and each of those people gets to eat one of these sandwiches. And then they rate on a scale from 1 to 10 how much they enjoyed the sandwich, with higher ratings indicating that they liked it more. What we've essentially done here is we've created 4 separate groups of people. One group that ate a crunchy grape sandwich, one group that ate a crunchy strawberry sandwich, one group that ate a creamy grape sandwich, and so on. However, the way that we created these 4 groups was by taking our 2 independent variables and looking at every possible combination of them. In statistics, this is called crossing the 2 variables. When we cross the 2 variables, we end up looking at every possible combination of them. So our first independent variable has 2 levels, crunchy versus creamy. Our second independent variable has 2 levels, grape versus strawberry. And if we multiply 2 times 2, it gives us the 4 different combinations of sandwiches that we can make with those ingredients. So again, let's say we were to do this study. We have our 4 different sandwiches. Each participant is going to eat and rate one of those 4 sandwiches. So we've effectively created 4 separate groups of people. In statistics terms, we would call this a 2x2 factorial design. This is the simplest kind of factorial ANOVA that we can do. The number of numbers tells us how many independent variables there are. So in this case, we have 2 numbers, a 2 and then another 2. And the fact that we have 2 numbers tells us there's 2 independent variables, or in other words, this is a 2-way design. The values of the numbers themselves tells us how many levels each of our independent variables has. So that first 2, the one before the x, tells us that we had 2 different kinds of peanut butter. The second 2, the one that comes after the x, tells us that we had 2 different kinds of jelly. And again, if we multiply 2 by 2, we end up with 4 different combinations, or 4 different sandwiches that we could make here. Each of those combinations is called a cell. So rather than thinking of them as separate groups, which they are, we're going to refer to them as cells in our design. Each of those cells is eventually going to have its own mean. So for the people who ate the crunchy grape sandwich, on average, how much did they like it? The people who ate the crunchy strawberry sandwich, on average, how much did they like it? We can calculate a cell mean for each of these 4 groups to start to get a sense of what sandwich people liked the best. As I mentioned a minute ago, the factorial ANOVA is essentially like 3 tests in one. It's going to tell us 3 separate things. Similar to an ANOVA that we learned 2 weeks ago, we're going to get an F statistic and a p-value that tells us about the significance of the thing that we're testing. However, since we're testing 3 separate things all at once, this test is actually going to give us 3 separate F statistics and 3 separate p-values. Here are the 3 things that a factorial ANOVA is going to tell us. First, it's going to tell us whether there is a main effect of independent variable 1. So if we ignore independent variable 2 completely, and we just focus on the first IV and the DV, the test will tell us whether there's an overall relationship between those 2 variables. Next, it'll do the same thing, but for the other independent variable. So if we ignore independent variable 1, we will test to see whether there's an overall relationship between independent variable 2 and our dependent variable. If we find an overall relationship, we would say that we found a main effect of IV2. Finally, we want to know if there is an interaction that involves all 3 of these variables. Maybe it's the case that the relationship between 2 of these variables depends on the third one, which is another way of saying maybe it's not either independent variable on its own, but the combination of both independent variables that affects our dependent variable. Let's see how this 3-in-1 situation plays out in our peanut butter and jelly study. The first thing we would want to do is test for a main effect of independent variable 1. Remember, in this example, independent variable 1 is type of peanut butter. So the first question that the factorial ANOVA will answer is whether there is a main effect of peanut butter type, our first independent variable. When we're testing for a main effect of peanut butter type, we're ignoring jelly, which is our other independent variable. For the purpose of this test, we don't care about jelly. We only care about whether there's an overall relationship between peanut butter and how much people like the sandwich. So statistically, what we're trying to answer is whether people overall liked one type of peanut butter better than the other. So in essence, what we're going to do is we're going to take these 4 separate groups and we're going to collapse them down into 2 groups. Any person that got crunchy peanut butter on their sandwich, regardless of whether they got grape jelly or strawberry jelly, those people are all going to get lumped together into one big group. We'll call them the crunchy group. Anybody who got creamy peanut butter, again, regardless of what kind of jelly they had, the creamy peanut butter people are all going to get lumped together into one group as well. So what we've essentially done here is taken our 4 groups and collapsed them down to 2. One group that got crunchy peanut butter, one group that got creamy peanut butter. What we'll then do is calculate an overall mean for the people who got crunchy peanut butter and an overall mean for the people who got creamy peanut butter. We'll compare those means against each other to see if there's an overall difference, in other words, an overall preference, for one type of peanut butter over the other. Did people consistently like crunchy better than creamy better than crunchy, or did they like them the same? When we do what I just described, take these 4 groups and collapse them down into 2 in order to test for a main effect, what we're doing is calculating what are called marginal means. So the people who ate crunchy grape sandwiches, they would have their own cell mean. The people who ate crunchy strawberry sandwiches, they would also have their own cell mean. But when we collapse those 2 groups together into one big group, those people have what we call a marginal mean. So in the diagram on the screen, we'd have a marginal mean for all of the people highlighted in brown, and we'd have another marginal mean for the combined group highlighted in yellow. Next, we're going to do the same thing we just did, but now we're going to test for a main effect of jelly instead of peanut butter. Jelly is our second independent variable. And when we're testing for a main effect of jelly, we're going to ignore peanut butter altogether. Because what we want to know is whether overall people liked one flavor of jelly better than the other one. Similar to what we did on the last slide, we're going to take these 4 groups and we're again going to collapse them down into 2 groups. But now, since we're testing for the other main effect, we're going to collapse them in the other direction. Anybody who had grape jelly on their sandwich, regardless of what kind of peanut butter they had, they're all going to get lumped together into one big group. Anybody who had strawberry jam on their sandwich is also going to get collapsed into one big group. So just like we did on the last slide, we will calculate an overall mean for the combined grape jelly group and an overall mean for the combined strawberry jelly group, compare those marginal means against each other, and see if people overall liked one kind of jelly better than the other, or if they liked them the same. The third thing this test will tell us is whether we found a statistically significant interaction. Remember that if we found an interaction, what that tells us is we have to know all 3 variables in order to fully understand this relationship, because the effect of one variable depends on the other one. When we're talking about interactions, we describe them as interactions between the 2 independent variables. So in this case, we would be testing to see whether there is a peanut butter times jelly interaction on how much people enjoyed eating this sandwich. Another way of thinking about this is maybe people's jelly preference might not always be the same. Maybe people's jelly preference actually depends on what kind of peanut butter it's paired with. For example, if I only have creamy peanut butter in my house, maybe I like the pairing of creamy with grape better than creamy with strawberry. But if I only have crunchy peanut butter in my house, I like strawberry jelly with crunchy peanut butter. I don't like grape jelly with crunchy peanut butter. So it's not each variable on its own, it's the combination of variables that's dictating how much a person is going to like this sandwich. We talked earlier about ANOVA language. The peanut butter and jelly example that we just talked about is a 2x2 design. The first two tells us that there were two different kinds of peanut butter. The second two tells us that there were two different kinds of jelly. How could we make this study instead a 3x2 or 2x3 design? What would we have to do to make that happen? What we would need to do is add a third level to one of our two independent variables. So for example, we could add a third type of peanut butter, maybe crunchy, creamy, and almond. That would turn this into a 3x2 design. Alternatively, we could add a third type of jelly. Maybe we stick with just crunchy and creamy peanut butter, but now we have grape, strawberry, or apple jelly. This would be a 3x2 or 2x3 design, and in either case, we have 6 different combinations of sandwiches that we could now make. So our study is getting more complicated, and we're going to need more participants. How could we make our peanut butter and jelly example a 2x2x2 design? Remember that the number of numbers tells us how many independent variables we have in our study. Previously, we only had 2. Now we have 3. So we call this a 3-way design rather than a 2-way design. So to take our 2x2 study and make it a 2x2x2 study, we would have to add a third independent variable that also has 2 levels. For example, in addition to manipulating the type of peanut butter and the type of jelly, what if we also manipulated the type of bread that we used? So what if I made 4 different sandwiches all on white bread and 4 different sandwiches all on wheat bread? Now I've got 8 different combinations of sandwiches I could make with these ingredients. 2 peanut butters times 2 jellies times 2 types of bread, 2 times 2 times 2 gives us 8 possible combinations. You can see how these studies can get complicated pretty quickly. Let's look at a few other conceptual examples of factorial designs and talk about the main effects and interactions that we might find in studies like these. In one recent study, they wanted to see what factors influence attendance rates at high schools. One of the variables that they looked at was comparing schools that require uniforms against schools that don't require uniforms to see if overall one type of school has better attendance than the other. Another factor they looked at was the socioeconomic status of the school. So they looked both at public schools and at private schools to see if there was overall differences in attendance between those two types of schools. So in this study, we have 2 independent variables. The first independent variable is whether the school requires a uniform or not. The second independent variable is whether the school is lower or higher SES students. Our dependent variable here is going to be the attendance rates for each school. So here's your uniform students and your non-uniform students. Here's your lower SES schools and your higher SES schools. So again, here we have a 2x2 design. We're looking at every possible combination of these 2 variables. We've got some low SES schools that require uniforms, some high SES schools that require uniforms, some low SES schools that don't, and some high SES schools that don't. So in a sense, we've got 4 different groups or 4 different types of schools whose attendance we're going to measure. Imagine that we did this study and we found that there was a main effect of SES. Low SES schools overall had higher attendance than high SES schools did. What exactly does that mean? And how would we come to that conclusion? Remember that when we test main effects, what we're doing is we're taking our 4 groups and we're collapsing them down into 2 groups. So in this example, if we wanted to test for a main effect of socioeconomic status, we would take all the low SES students and combine them into one group, and take all the high SES students and combine them into one group. So now, regardless of whether they wear a uniform or not, we've collapsed our groups down into two. We've got our low SES students and our high SES students. We can calculate a marginal mean for each of those combined groups and compare them to see if, in fact, low SES students overall have better attendance than high SES students do. What about our other main effect? Imagine we ran our study and we found that there was not a main effect of uniform. What does that mean, and how would we figure that out? Again, since we're testing for a main effect, what we're going to do is we're going to take these four groups and we're going to collapse them down into two. Now we're going to collapse them the other way. So all of the students that wear a uniform to school, regardless of their socioeconomic status, they're all going to get collapsed together into one big group. That's the blue slide, the blue group on the slide. All the students that don't wear a uniform, again, regardless of their SES, they're all going to get lumped together into the big yellow group on the slide. We can then calculate a marginal mean for the blue group, a marginal mean for the yellow group, and compare the two. If there's no main effect of uniform, what that's telling us is that overall, the students who wear a uniform and the students who don't have equally good attendance. Finally, imagine that we found an interaction between uniform and socioeconomic status. What does that mean? What it tells us is that the effect of uniform on attendance is different for low SES schools versus high SES schools. For example, maybe we find that students who wear a uniform have better attendance, but only if they go to a low SES school. In a high SES school, maybe uniform doesn't make any difference. Here's the actual results of the study that this example is based on. Look at the last line of their abstract. What they say was that they found some indication that low-income students in schools that required uniforms demonstrated better school attendance than low-income students in schools that did not. So their goal in studying this was to see if overall wearing a uniform improved attendance. What they found was that the effect of wearing a uniform was a little more complicated than that. Wearing a uniform did improve students' attendance, but only in low SES schools, not in high SES schools. In other words, if we look just at low SES schools, students who wore uniforms had better attendance than students who didn't. But if we look just at high SES schools, wearing a uniform didn't make a difference. It had no effect on attendance. Another simple example of this. In this study, they wanted to see how wearing makeup affects a woman's perceived age. So the overarching question here was, does wearing makeup make women look younger? Here's the design of their study. They created these 8 different photos by crossing 2 variables. One of those variables was the actual age of the woman in the photo. So here we have a woman who's either 20 years old, 30 years old, 40 years old, or 50 years old. For each of those women, we have 2 pictures of her, one without makeup and one with makeup. That's our other independent variable. So what we have here is a 2x4 factorial design. The 2 corresponds to makeup. They're either wearing makeup or they're not. The 4 corresponds to age because we included 4 different age groups, 20, 30, 40, and 50, in this study. So each participant in this study looked at one of these 8 photos, and the dependent variable was their estimation of how old the woman in the photo was. The first thing we do in this study is test for a main effect of makeup. Since we're testing for a main effect, what we're going to need to do is combine our groups together. Specifically, all of the women who weren't wearing makeup, we'd combine them into one big group, and all of the women who were wearing makeup, we'd combine them into a second big group. What we could then do is calculate a marginal mean for each of these two groups. On average, how old did people think the no makeup woman looked? On average, how much did people think the makeup wearing woman looked? We'd compare those two marginal means to see if there was in fact a main effect of makeup. If there was a main effect of makeup, what that would suggest is that overall, women who were wearing makeup were perceived as younger compared to women who were not wearing makeup. Our other independent variable is age. We have 4 age groups here. So to look for a main effect of age, what we're going to have to do is create a marginal mean for each of the 4 age groups. Now, this example is more complicated than anything we're going to do in our class. We're going to focus just on 2x2 designs. But since this is a 2x4 design, what we'd end up with here is a marginal mean for women who were actually 20, 30, 40, and 50 years old, to see if overall women who actually were older were perceived as older. Most interestingly, we can look at the interaction between our 2 independent variables, makeup and age. What the interaction would tell us is if wearing makeup has the same impact on a woman's appearance, regardless of her age, or if the effect of makeup on a woman's appearance depends on how old the woman is. In this study, that's exactly what they found. What this graph is showing you is for each of the 4 age groups, 20, 30, 40, and 50 years old, how old was that woman perceived to be in comparison to how old she actually was. You see that some of the bars stick above the axis, some of the bars don't leave the axis at all, and other bars stick below the axis. What happened in this study is that if a woman was 20 years old and wearing makeup, she was actually perceived as older than a 20-year-old who wasn't wearing makeup. For 30-year-olds, wearing makeup had no effect whatsoever. They were perceived as the same age regardless of whether they were wearing makeup or not. For older women, particularly for 50-year-olds, a 50-year-old wearing makeup was perceived as younger than a 50-year-old who was not wearing makeup. So the takeaway message from this study is that the effect of makeup on a person's appearance depended on that person's actual age. For women who were younger, only 20 years old, wearing makeup caused them to look older. But for women who were actually older, say 50 years old, wearing makeup caused them to look younger. This is a perfect example of what we mean when we say interaction. The effect of one variable, makeup, depended on another variable, which was the woman's actual age. One more conceptual example of how factorial designs work. In early social psychology, one of the most basic questions that psychologists wanted to answer was how the presence of an audience affected people's performance. Do we do better when other people are watching us? Or do we do worse when other people are watching us? In some early studies, they found that people actually did better when people were watching them. For example, when they were asked to trace a dot on a moving table, or when they were asked to solve simple math problems, they did better in front of an audience than when they did those same things alone. So psychologists started to think, well, maybe what being watched by an audience actually improves people's performance. Soon after that, however, a number of studies came out that showed the exact opposite. When they had people memorize lists of nonsense words or complete complicated mazes in front of an audience or alone, people actually did worse when they were being watched and did better when they were by themselves. So which is it? Does performing in front of an audience make us do better? Or does performing in front of an audience make us do worse? Maybe you have some personal experience with this. If you've ever been a performer of any kind, like a musician, a dancer, an athlete, an artist, an actor, do you think you perform better when you're practicing on your own or when you're practicing in front of a crowd? After many, many more studies, psychologists ultimately decided that it depends. In other words, the effect of an audience isn't always the same. It's not always straightforward. Here's the name of the psychologist who reconciled this research and the theory that he developed. He said that there is in fact a relationship between the presence of an audience and how well we perform, but that relationship depends on something else. Specifically, that relationship depends on the difficulty of the thing that we're doing. Now, by difficulty, it may mean how objectively hard or easy that thing is, or it may mean how subjectively easy or difficult it is for us. That is to say, whether we're good at it or bad at it. So what this psychologist theory said was that if the task that we're doing is something that is easy, having an audience leads us to perform better. But if the task that we're doing is something that is difficult, having an audience makes us perform worse. So the effect of the audience on our performance is different depending on that moderating variable, the difficulty of the task. Look back at the old research that we just talked about a minute ago. These tasks on the left, tracing a dot and solving simple math problems, those are pretty easy tasks. So it makes sense that people did better when they were in front of an audience. Those other tasks, memorizing nonsense words and doing complicated mazes, those are harder tasks. So it kind of makes some sense that since the tasks were harder, having the audience made people do worse. Now, the psychologist who developed this theory went one step further than that. He said that this theory not only applies to humans, but it applies to all animals. That the presence of an audience affects us all the same way, and it depends on the difficulty of the thing that we're doing. So to test his theory, he didn't want to just use undergraduates like everybody else. He went out and got himself a sample of 72 adult female cockroaches to serve as his participants. And what he did is he built two different mazes for the cockroaches to run through. The first maze he called a simple maze, and it was just basically a straight line. So you put the cockroach in the maze, you shine a flashlight at the starting point, the cockroach runs away from the light, and he measured how quickly they were able to get out of the maze. That was our dependent variable. He also created a complex maze that was kind of like a four-way intersection. So again, he puts the roach in at the starting point and turns on a flashlight behind it. The roach runs away from the flashlight, but the roach has to get to the intersection and choose the correct way out in order to successfully complete the maze. For that reason, you'd probably expect roaches to take longer to complete the complex maze as opposed to the simple maze. Then he went and built two more mazes. He built another simple maze, and he built another complex maze. But in these mazes, what he did was he built in little windows, so that when a cockroach ran through the maze, they were actually doing it in front of an audience of other cockroaches. So what you're seeing on the screen right now is an illustration of the 2x2 design of this study. Every roach in this study ran either the simple maze or the complex maze. So that's our first independent variable. Whichever maze they did, they either did it alone or they did it in front of an audience. That's our other independent variable. So we've got four possible combinations here. Some roaches ran the simple maze alone. Some of them ran the simple maze with an audience. Others ran the complex maze alone. And still others ran the complex maze in front of an audience. Our dependent variable here is how quickly the roaches were able to complete the maze. Keep in mind, for this dependent variable, higher scores mean the roaches did less well, meaning it took them longer to get out. The first thing that the researchers found, as one would expect, was a main effect of maze type. So when he collapsed those four groups down into two and looked at the marginal means for roaches that ran the simple maze versus roaches that ran the complex maze, what he found, not surprisingly, was that roaches took longer to get out of the complex maze. Now let's look at the interaction. In the simple maze, since it's an easy task, if the theory is correct, we would expect that the presence of an audience would enable roaches to do better, meaning they would escape the maze faster. If we look just at the roaches that ran the simple maze, that's exactly what they found. Roaches who ran the simple maze got out faster if they had an audience compared to if they didn't. For the complex maze, we would expect the opposite pattern. Having an audience should hurt performance because it's a difficult task. So we would expect roaches to take longer to get out of the complex maze if they had an audience. And that's exactly what the researchers found. When roaches ran the complex maze, they got out about a minute faster on average if they didn't have an audience than if they did have an audience. So these findings are all consistent with the theory. For a simple task, running the simple maze, having an audience helped performance. It helped the roaches get out faster. However, for the more difficult task, the complicated maze, having the audience hindered roaches' performance. It took them longer to get out if they had an audience. Here are the actual results of this study. This table shows us the cell means for each of these four groups. So what they called the runway is what we called the simple maze, and what they called the maze is what we called the complex maze. The alone is, of course, they did it by themselves. The social is the group that did it in front of an audience. Running time is the dependent variable we were interested in. That's how long it took them to get out of the maze. Notice down here, this is what our output is going to look like for this test when we look into SPSS momentarily. I promised you earlier, since we're testing for three separate things, 2 main effects and 1 interaction, we're going to get 3 separate F statistics and also 3 separate p-values. Here are those 3 F statistics for this particular study. Notice the F statistic for the first independent variable, which is whether they were alone or not, that one was not significant. However, there was a significant effect of maze type. We saw earlier that overall, the simple maze was easier, faster to complete than the complex maze. But most importantly, there was also a significant interaction between the 2 independent variables. The effect of the audience depended on the type of maze. Let's now look at how to perform this test in SPSS. It's almost Christmas time, so it's time to do your gift shopping and time to do your gift wrapping. And if you're like me, you're probably not too good at wrapping gifts neatly like the one on the left. Yours probably come out looking more like the one on the right. These researchers wanted to know if how a gift is wrapped affects how much people like the gift. Do people like the same gift more if it's wrapped neatly as opposed to if it's wrapped in a sloppy way? They also wanted to see if what matters more, or just as much, is what's inside the box. Maybe, for example, I don't care how the gift is wrapped if it's something that I like, but if the gift is something that I don't like, maybe I do care how the gift is wrapped. If that's the case, we would find an interaction. We would need to know all 3 of these variables in order to know the whole story. So here's what these researchers did. They did 2 studies. In study 1, they recruited 180 fans of the Miami Heat basketball team, and they gave them a gift that was either desirable or undesirable. Some of those gifts were wrapped neatly, and some of them were wrapped sloppily. The desirable gift was a mug of their favorite team, the Miami Heat. The undesirable gift was a mug of a team that they're not a fan of, the Orlando Magic. So again, here we have a 2x2 factorial design. Every person who participated in this study got a gift that was either wrapped neatly or wrapped sloppily. And then when they opened the box, the gift that was inside was either something desirable or something undesirable. At the end, each participant rated on a 1 to 9 scale how much they liked the gift, with high numbers indicating that they liked it more. So again, here's how we would describe this design. The first two corresponds to how the gift was wrapped. The wrapping was either neat or sloppy. The second two corresponds to whether the gift was desirable or not. Take a note of this sentence on the screen, because anytime we write up our answer for a question like this, our first sentence of our write-up is going to look like this one. It's going to lay out all of our variables and all of the different levels of those variables in a concise way. The data file for this study is called giftwrap1.sav. For each participant, we know three things. First, we know whether the gift that they got was wrapped neatly or wrapped sloppy. Second, we know whether the gift that they got was desirable or undesirable. Third, we know how much they liked that gift, which they self-reported on a 9-point scale. To run this test, we're actually going to go into the very same menu that we used to run the Between Groups ANOVA 3 weeks ago. Here is what that menu looks like under Analyze, General Linear Model, Univariate. Just like we did 3 weeks ago, we're going to put our dependent variable in the dependent variable box. In this case, that's how much they liked the gift. We're now going to put not one, but both of our independent variables in the fixed factors box. So IV1, how the gift was wrapped, and IV2, whether the gift was desirable or not, both of those variables are going to go in the fixed factors box. Just like we did a few weeks ago, we're also going to dip into the options menu. We're going to ask SPSS to give us descriptive statistics. We're also going to ask SPSS to give us estimates of effect size. Here are the two parts of our output that we need. The first table gives us the descriptive statistics, which we'll take apart in just a second. The second table gives us the results of our inferential tests. Those three things that we're testing for, the two main effects and the interaction, all of those things are going to be explained in the table at the bottom. So let's now go through those three things one at a time and talk about whether we did or did not find significant main effects or interactions in this example. The first independent variable is how the gift was wrapped. So if we want to know if there was a main effect of wrapping, what we really want to know is if overall people had a preference between the sloppy gift and the neatly wrapped gift, ignoring whatever was inside the box. Look down at the tests of between subjects effects table at the bottom of the screen. Notice the 3 rows in the middle of that table. We have one row for each of our independent variables. So there's a row called wrapping and there's a row called desirable. Below that, we have a row with both of our independent variables, wrapping times desirable. That's the row that tells us about our interaction. We'll come back to that one. For now, since we're testing for a main effect of wrapping, we want to look at the row titled wrapping. The p-value in that row is 0.029, which is less than 0.05. What that tells us is that we have in fact found a main effect of wrapping. So overall, people did have a preference between the neatly wrapped gift and the sloppy wrapped gift. Now, before we figure out what exactly that preference was, one other thing I want you to notice is, as with all of the other ANOVAs that we've learned so far, we're going to include not one, but 2 different degrees of freedom values here. The first one, which in this case is 1, is going to be the degrees of freedom value that is in the same row as the wrapping variable. The second one is going to be our error degrees of freedom, which in this case is 176. In addition to our p-value of 0.029, we're also going to need to include the F statistic for this main effect, which was 4.87, in our answer as well. Now let's interpret this main effect. All we know so far is that there was a main effect of gift wrapping. So overall, people's ratings of the neatly wrapped gift and people's ratings of the sloppy wrapped gift were different from each other. But which one did people like better? If we look at the descriptives table up at the top, we'll see that there's a row for each combination of our two independent variables. So the first row, for example, tells us the mean for neatly wrapped gifts that were undesirable. The second row tells us the mean for neatly wrapped desirable gifts. What we want to hear is the third row, which is the total mean for the neatly wrapped gifts. On average, people who got a neatly wrapped gift rated it as a 5.63 out of 9 in terms of how much they liked it. Right below that, we get the same number for sloppy wrapped gifts. Sloppy undesirable, sloppy desirable, and then most importantly for our purposes right now, sloppy total. People who got sloppy wrapped gifts, their average rating was a 6.26, which is higher than the rating for neatly wrapped gifts. So what this tells us is we found a main effect of wrapping. Overall, regardless of what was inside the box, people actually liked the sloppy wrapped gift better than the neatly wrapped gift. Let's now do the same thing, but for the other independent variable, which is what was inside the box. Was there a main effect of desirability? So if we ignore how the gift was wrapped, did people overall like one gift better than the other? As you might expect, their hypothesis was that people would like the desirable gift better than the undesirable gift. To find the main effect in the bottom table, we're going to look in the row called desirable, immediately scan over to the p-value, which here we see is very, very small. That tells us that we did find a main effect of desirability. Which of the two gifts did people like better? To answer that question, we go back up to the descriptive statistics table, and we have to find the total means for the two different types of gifts. Those can be found at the bottom of this table. So the total mean for undesirable gifts was 4.51, and the total mean for the desirable gift was 7.38. As we expected, regardless of how it was wrapped, people liked the desirable gift better than the undesirable gift. What about the interaction? Did we find one here? And if so, or even if not, what does that tell us? Remember that we phrase interactions in terms of an interaction between the two independent variables. So here we would call this a wrapping by desirability interaction. What we really are trying to figure out here is whether people's liking of the gift depended on both how it was wrapped and what was inside the box. However, if we look at the interaction row of that table at the bottom, we see a very big p-value, 0.875, which tells us that we did not find a significant interaction here. Now, what exactly does that mean, that we didn't find a significant interaction? Let's look at our cell means in the table at the top. First, let's look just at undesirable gifts. If a person got an undesirable gift that was wrapped neatly, they rated it as about a 4.2. If people got an undesirable gift that was wrapped sloppily, they rated it as about a 4.8. So if we compare those two numbers, what we can say is that if a gift was undesirable, wrapping it sloppy made people like it about 0.6 points more. In purple are the two cell means for the desirable gifts. So if the desirable gift was wrapped neatly, the rating was about a 7. If a desirable gift was wrapped sloppy, the mean rating was about a 7.7. So for desirable gifts, sloppy wrapping made liking go up by about zero 0.7 points. The reason we didn't find a significant interaction here is that the type of wrapping is having the same effect regardless of whether the gift is desirable or undesirable. In other words, if we look just at the undesirable gifts, people like the sloppy wrapping a little bit better. If we look just at the desirable gifts, people again liked the sloppy wrapping a little bit better. So the effect of sloppy wrapping was the same regardless of whether the gift was desirable or undesirable. Remember that the word depends on is usually a big hint when we find an interaction. In this case, however, the effect of wrapping did not depend on whether the gift was desirable or undesirable. Gift wrapping actually had the same effect for both undesirable gifts and desirable gifts, which is why we didn't find a significant interaction. How would we write up our results for a problem like this one? Since this test is testing 3 separate things, our write-up is going to be 3 times as long as it has been in the past. But if we think about it as 3 separate sections, what we're really doing is the same thing we've been doing all along, just more of it. The one new thing we're going to add is a sentence at the beginning of our write-up that explains all of the variables and levels and the design of our study. For this example, that sentence would look something like this. A 2x2 ANOVA was performed on participants' ratings of how much they liked the gift. Again, you don't need to get creative here. You can always say a 2x2 ANOVA was performed on blank, where blank is whatever the dependent variable was. Next to each of the numbers in parentheses, we're going to write the name of our independent variable, and we're going to list out the different levels of that independent variable. For example, wrapping was our first independent variable, and it had 2 levels, neat or sloppy. Then what we'll do is we'll go through each of those 3 things that we just tested and explain each one, including whether it was or wasn't significant, and include any means or other information that we need to explain how we interpreted that effect. The first thing we tested was the main effect of wrapping, and we did find a main effect of wrapping. When we looked at the marginal means, what we found was that overall, people liked the sloppy gift better than the neat gift. What you're seeing here are the F-test results for the main effect of wrapping, as well as the marginal mean and standard deviation for the sloppy gift, and the marginal mean and standard deviation for the neatly wrapped gift. The second thing we tested was a main effect of desirability. What we found was that there was a main effect, and overall, people liked the desirable gift better than the undesirable gift. Here again are the F-test results for that main effect, as well as the marginal means and standard deviations for the overall desirable and overall undesirable groups. Finally, we did not find a significant interaction between our 2 independent variables, wrapping and desirability. We'll report the F-test results for that interaction, showing that it wasn't significant, and then we should offer a brief explanation of what exactly that means. The fact that we didn't find an interaction here tells us that the type of gift wrapping had the same effect on people's liking, regardless of whether the gift was desirable or undesirable. In other words, no matter what kind of gift they got, desirable or not, people liked the sloppy wrapping a little bit better than they liked the neat wrapping. Here's how the authors wrote up their results in their published paper about this study. Notice they did a 2-way ANOVA with wrapping neatness as their first independent variable and gift desirability as their second independent variable. Their dependent variable was what they called gift-related attitudes, in other words, how much people liked the gift. they found two significant main effects in the same way that we just did, and they found no significant interaction, nor did we. The way that they explained that interaction, or lack thereof, was to say that wrapping neatness affected attitudes in the same way, regardless of gift desirability. Here's the second study that these authors did. Again, they wanted to compare neatly wrapped gifts against sloppy wrapped gifts. But instead of changing what was inside the box, what they changed is who gave us the gift. Was the gift given to us by a close friend, or was it given to us by someone who we don't know that well? Maybe our preference for one type of gift wrapping versus the other depends on who's giving us the gift. So in one of their follow-up studies, what they did is they had participants imagine getting a gift that was either wrapped neatly or wrapped sloppily, and that gift was given to them either by someone who they don't know that well or someone who they know very well, from either an acquaintance or from a friend. Again here, we've got a 2x2 design. If we cross those two variables, we have 4 different combinations. A neat gift from an acquaintance, a neat gift from a friend, a sloppy gift from an acquaintance, or a sloppy gift from a friend. As in the previous study, each participant rated on a scale from 1 to 9 how much they liked the gift. The data from this study are in the data file giftwrap2.sav, and again, we know 3 things about each of these participants. How was the gift wrapped, sloppy or neat? Who gave it to them, a friend or an acquaintance? And how much did they like it on a scale from 1 to 9? To run this 2x2 factorial ANOVA, we're going to go back to analyze general linear model univariate. Our dependent variable is the same as it was before, how much people liked the gift. Just like we did before, we're also going to put both of our independent variables, how the gift was wrapped and who gave it to them, in the fixed factors box. And in the options menu, we're going to ask for descriptive statistics and effect size. Here are those same 2 tables that we saw before. The top one gives us our descriptive statistics, including both our cell means and our marginal means. The bottom one gives us the results of our f-tests for both main effects as well as for the interaction. First, let's test for a main effect of wrapping. Like we did before, we'll go to the bottom table, find the wrapping row, and look for the p-value for that main effect. It was almost significant, but not quite there. P equals 0.06. So our conclusion is going to be that we did not find a main effect of wrapping in this study. To find the marginal means, we're going to look at the top table. We have a total mean for the neatly wrapped gift and a total mean for the sloppy wrapped gift. The fact that those numbers are not significantly different, we know because the p-value for the wrapping main effect was not significant, 0.06. So even though neat had a mean of 5.58 and sloppy had a mean of 5.13, the main effect of wrapping, or lack thereof, tells us that those numbers are not significantly different. So our conclusion is going to be overall, people liked the neatly wrapped and the sloppy wrapped gifts equally the same. What about our other independent variable? Was there a main effect of who gave us the gift? The variable we called relationship, or giver. If we find the giver row in the between subjects effects table, we see a big p-value, 0.907, which tells us that overall, people liked the gift the same, regardless of whether it was a friend or an acquaintance who gave it to them. Here are the marginal means for those 2 combined groups. People who got a gift from an acquaintance had a mean of 5.34. People who got a gift from a friend had a mean of 5.36. And again, those means are not significantly different. So our conclusion here is going to be people liked the gift the same amount, regardless of whether the gift came from a friend or from an acquaintance. Lastly, we're going to test for an interaction between our 2 independent variables, wrapping and relationship, or giver as it's called in SPSS. We'll find the interaction row in the bottom table, and we see that the p-value here was significant. So we did find a significant interaction. What we know so far is that because the interaction is significant, that the effect of wrapping on how much we liked the gift depended on who was giving us the gift. But we don't yet know exactly how all three of these variables related to each other. So what does it mean for there to be? Let's look at the numbers here to make sense of this interaction. So if an acquaintance gives you a gift, and that gift is wrapped neatly, people liked it. The mean was about 7. But if an acquaintance gave you a gift and the gift was wrapped sloppily, people didn't like it so much. The mean was down at 3.74. So if you're getting a gift from an acquaintance, people prefer the gift if it's wrapped neatly compared to if it's wrapped sloppy. Let's look now at the purple numbers, which, as we'll see in a second, show the exact opposite pattern. If you get a neatly wrapped gift from a friend, you don't like it so much. The mean was about 4.18. But if a friend gives you a sloppy gift, you actually like it more, a mean of 6.48. So you can see how the orange numbers and the purple numbers move in opposite directions. If we're getting a gift from an acquaintance, we like it better if it's wrapped neatly. But if we're getting a gift from a friend, we like it's better if it's wrapped sloppy. Again, I didn't realize this until just now, but those words on the right-hand side, those are mistaken. Those are saying the opposite of what the numbers actually show. If the gift came from an acquaintance, people actually preferred the neat wrapping. But if the gift came from a friend, people preferred the sloppy wrapping. The takeaway message here is that people's preference for neat versus sloppy wrapping was different depending on who it was that was giving them the gift. That's why we can say we found a significant interaction. What's our write-up going to look like for a problem like this one? Again, make sure you always include that sentence at the beginning to explain all of the variables involved as well as the levels. So here we again did a 2x2 ANOVA on participants' ratings of how much they liked the gift. The only difference from the previous example is our second independent variable is now relationship, friend versus acquaintance. We did not find a main effect of wrapping. Overall, people liked the sloppy and neatly wrapped gifts the same. We didn't find a main effect of relationship either. People overall liked the gift the same, regardless of whether it came from a friend or from an acquaintance. However, we did find a significant interaction, so we need to try to explain that interaction. Next week, we're going to talk about ways to explain interactions in a more precise way, by not only including graphs to display the interaction, but also performing additional tests to break the interaction down into pieces and make sense of those individual pieces. Here we would say something like, if the gift came from a friend, people liked the sloppy wrapping better, but if the gift came from an acquaintance, people liked the neat wrapping better. In other words, people's liking of the gift was determined both by how it was wrapped and by who gave it to them. Here are the actual results of this study. Notice they presented all of their results in a table. For the two main effects in the interaction, this table shows us the F statistic, the degrees of freedom values, the p-value, as well as the eta squared effect size. They also displayed the interaction in a graph, showing that if the gift came from an acquaintance, they liked it neatly wrapped, but if the gift came from a friend, they preferred that it be wrapped sloppily. Here's how they described their interaction. Gift-related attitudes are more favorable when a friend gives a sloppy gift, but when an acquaintance gives a neat gift. So when you're giving a gift to a friend, what we can learn from this is you might actually want to wrap it kind of sloppy. But if you're giving a gift to someone who you don't know as well, you want to take the time to make sure it's wrapped really neatly. Let's quickly review the concept of interactions. Remember, when we find an interaction, what we're saying is that the relationship between two variables depends on some other variable. Here are the 4 examples that we've talked about so far today. First, drawing a smiley face on the check does affect the size of a tip that servers get. But as it turns out, that relationship only exists for women servers, not for men. Wearing school uniforms predicted the frequency of absences at schools. But that relationship depended on the kind of school that we were talking about. Schools that require uniforms have fewer absences, but only for low SES students. The presence of an audience affects people's performance, but it affects performance differently depending on the difficulty of the task. If the task is easy, having an audience makes performance better, but if the task is difficult, having an audience makes performance worse. Finally, how a gift is wrapped affects how much we like the gift, but that relationship depends on how well we know the person who's giving us the gift. If the person's a friend, we like the messy gift better, but if the person's an acquaintance, we don't know him that well, we like the neatly wrapped gift better. These top two examples, the smiley face and the school uniforms, in each case, what we found is that there was a relationship for one group, but not for the other group. So for the smiley face example, smiley face had an effect on tips for women, but did not have an effect on tips for men. For uniforms, uniforms predicted absences for low SES students, but uniforms had no effect on absences for high SES students. These are examples of what we would call ordinal interactions. An ordinal interaction means that we found a relationship for one group of people, for example, women, but we found no relationship for the other group of people, for example, men. The other two types of interactions that we've talked about were different in nature. We found relationships for both groups, but those relationships were in opposite directions. So for the audience, having an easy task, for the easy task, an audience helped performance. For a difficult task, an audience hurt performance. For friends, we liked sloppy wrapped gifts better, but for acquaintances, we liked neat gifts better. These are examples of what we would call disordinal interactions. So on the last slide, an ordinal interaction means we found an effect in one group, but no effect in the other group. In contrast, a disordinal interaction means we found an effect in one group and the opposite effect in the other group. I want to leave you today with a few practice problems to mull over for next week. This study looked at whether being ostracized, aka socially excluded, makes people feel sad. However, these researchers also hypothesized that that effect might depend on whether that person has consumed alcohol or not. In other words, maybe being excluded makes us feel sad, but only if we haven't been drinking, not if we have been drinking. In this study, participants came into the lab and they drank either 4 shots of vodka or 4 shots of cranberry juice. So in other words, some people got alcohol and some people didn't. Then, participants played an online game called Cyberball. For those who aren't familiar, Cyberball is an online simulation where you're led to believe that you're throwing a ball around, playing catch, with a number of other participants who are sitting in other rooms. Some people are made to feel included, meaning the other people sometimes throw them the ball, sometimes don't. Some people, however, are made to feel excluded. They can see the other people throwing the ball, but they never get the ball thrown to them. So we again have a 2x2 factorial design. Each participant either drank vodka or drank juice, and then they played a game in which they were led to feel either socially included or socially excluded. Our dependent variable here, which they completed at the end of the study, was a measure of their mood. The data for this example are in the file ostracized.sav. For each participant, we know whether they were socially included or excluded. That's our first independent variable, which is called ostracized in the file. We also know whether they drank juice or vodka. That's our second independent variable, which is called alcohol. Finally, we know their mood, which is a variable called NTS mood. Here's how we would set up this analysis. Again, we're going to go to Analyze General Linear Model Univariate. We're going to put both of our independent variables, ostracism and alcohol, in the fixed factors box. And we're going to put our dependent variable, which was mood, in the dependent variable box. Be sure to check descriptive statistics in the options menu as well, so that we can get the means that we need to interpret these findings. Here are the results, descriptives at the top, inferential statistics at the bottom. Following the same procedure that we used for the gift wrapping problems, what I want you to do is first, in one sentence, explain the design of this study, including both independent variables, all of the levels of those variables, and the dependent variable. Then I want you to go through this output, and I want you to tell me whether or not there was a main effect of ostracism, and if so, what that means. Was there a main effect of drink? Explain what that means. And finally, tell me whether there was an interaction between alcohol and ostracism on people's mood. Try to pick out the numbers from the output, interpret them correctly, and once you're confident that you've understood what they mean, try to write up your results in APA format. The answer will be on the slides so that you can check your own answer when you're done, but we can also go over the answer at the start of our next class. One other study that you can use as an example to practice. This study looked at a phenomenon called romantic red, which is the belief that merely seeing the color red makes things appear more attractive to us. If you've ever been to the Valentine's aisle at Target, you know what I'm talking about. People associate red with romance. But does seeing red actually make a person appear more physically attractive? That's what these researchers wanted to test. So in their first study, they recruited a sample of only men. They brought men into the laboratory, and they showed them a picture of a woman, and they asked them to evaluate how physically attractive they found that woman. The catch was, some of those men saw a picture of the woman on an all-white background. A second group of men saw the same picture of the same woman, but on an all-red background. Then they rated the attractiveness of the woman on a scale from 1 to 9. Which of the tests that we've learned previously would you have to use to compare the mean rating of the white photo men against the mean rating of the red photo men? That's right. It's an independent t-test, because we'd be comparing two separate groups of men to see if their means are different. In this case, that's what these researchers did, and they found a significant difference. Overall, men who saw the woman's photo on a red background rated the woman as more attractive, compared to another group of men who saw the same photo on a white background. So what these researchers then wanted to do was run a second study. The first study suggested that men liked the red photo better than the white one. But what about women? Would women participants show this same preference? Or would they show a different preference? Or maybe no preference between the two photos? So they replicated what they did in study 1. They had one group of men look at a photo on a white background, and a second group of men rate a photo on a red background. But now they also included two groups of women. One group of women saw the white photo, and another group of women saw the red photo. So we again have a 2x2 factorial design. Our first independent variable is the photo color, red versus white. Our second independent variable is the sex of the participant, men and women. And our dependent variable is how attractive they found the woman in the photo to be. If we find an interaction here, what that's telling us is that color has a different effect on men than it has on women. Maybe, for example, men like the red photo better, but women like the two photos the same. Or maybe women actually liked the white photo better, in which case we would find a disordinal interaction. For practice on your own, you can use the data file romanticred.sav to try running this 2x2 ANOVA and writing up the results. Here's a screenshot to get you started in terms of which variables to put where. Remember that in the options menu, we need to select descriptive statistics as well. Here's the output for this test, which you can use to test for a main effect of color, a main effect of sex, as well as a sex by color interaction. You can try writing up your results for practice. When we meet again next week, we can go over these practice problems. We'll also look at a few more examples, including additional examples of interactions, and talk about some more sophisticated ways we can go about making sense of an interaction, including breaking it down into pieces and making a graph of it to help us visualize how the effect of one variable depends on another one.